Hello, welcome to my video covering electrons bound on superfluid helium. First, I'd like to cover the motivation behind this kind of qubit and why it's beneficial to the overall quantum computing scheme. Superfluid helium is expected to be a good medium for qubits because of its low sources of decoherence. Because the fluid is uniform, we don't have to worry about any local magnetic fields disturbing our system. The interaction between the electrons and the helium is also weak, which further leads to longer coherence times. The real limiting factor for these systems is phonon interactions, but are still expected to be longer when compared to other condensed matter-based schemes for quantum computing. But beyond this, they also have the ability to move through physical space. Because the electron is only bound in one direction, we can still move it from point A to point B laterally. This makes these electrons ideal for a flying qubit, which would couple to other subsystems. With a temperature requirement already in place by the superfluid helium, it makes more sense to couple this kind of system with superconducting qubits, which are also at lower temperatures. The electrostrictive binding of electrons onto liquid helium was first demonstrated in 1966 by Bruschi and colleagues, and later it was theorized by several groups in 69 and 70 that electrons feel a weak attractive charge from the dielectric liquid, but they can't enter the fluid because of a roughly 1 electron volt barrier caused by the hardcore repulsion. In the late 90s, people started looking at it as a potential quantum computing scheme. In 1999, Platzman and Dykman claimed that almost insurmountable technological and scientific barriers existed for quantum computing schemes such as NV centers. I won't cover their particular scheme in detail since it's more basic compared to the more recent designs, but essentially they make use of control plates underneath the superfluid helium to confine and manipulate the electrons. They proved that at millikelvin temperatures, they could perform operations in nanoseconds over coherence times of hundreds of microseconds. This design philosophy with control electrodes underneath the fluid has been utilized in various groups over the last 2.5 decades. In 2011, Bradbury and colleagues fabricated a design with 120 channels in the hopes of transporting qubits across the surface of the helium. Their group was primarily concerned with the high number of qubits needed to run between subsystems for error correction. Their design consisted of detection gates underneath the fluid that allowed them to move the electron packets over a two-dimensional distance equivalent to 9 kilometers with no detectable transfer errors. Their design was primarily limited by the RC rise time in the cryostat wiring, which affects the maximum speed the electrons could travel and ultimately how much decoherence they acquire before coupling to something else. However, the design that I'd like to dive deeper into was made more recently by Koolstra, Yang, and Schutzer in 2019. Their group was more concerned with manipulating the electrons on the surface of superfluid helium as the qubits themselves. Their design is more complicated, but it's easier to integrate the transportation aspect back in than it is to manipulate the quantum state in the previous schemes. They demonstrated that the coupling of electron clusters on a helium to a microwave cavity and could control the number of electrons on the island, allowing them to probe the Wigner molecule phase as well as the coherent control of a single electron. They started by depositing electrons through thermal emission from a tungsten filament and a DC bias voltage of 0.6 volts. Isolating individual electrons from the reservoir was achievable using the 3 sets of electrodes near the tip of the resonator. Making use of the fact that the electron-electron interactions causes them to be at least 200 nanometers apart, they could separate them using the appropriate voltages to trap only one. With a single electron in the resonator, they could investigate the properties of the electron by tuning the trap voltage. The orbital frequency crossed at a trap voltage around 0.184 volts, where there was a rapid change in delta F0. They were able to obtain a single electron-photon coupling strength and electron line width that are large compared to the resonator line width, indicating that each photon measures the presence of an electron, and the coupling is similar to that in semiconducting quantum dot CQED architectures. The anharmicity is also similar to superconducting qubits, meaning they could use the single electron as a qubit if they reduced the line width. They proposed that increasing the coupling strength and entering the strong coupling regime would allow for direct measurement of the electron orbital frequencies using two-tone spectroscopy. Since the orbital frequencies span tens of gigahertz, it would require a microwave resonator which could be embedded in the device. But to reach the strong coupling regime in future electron on helium systems, the vibrations of the surface of the helium would need to be reduced. They claimed that the preliminary simulations of a dot with less sensitive electrode geometry shows a 100-fold reduction in line width. This, along with controlled magnetic field gradients, would give control over an electron spin. Based on other more recent papers I've glossed over, it appears that the vibrations on the surface of the helium are the primary source of error and leave the most room for improvement. But what I think also needs to be addressed is the ability to couple the electron on helium spin state to another qubit. Performing operations on electron on helium qubits directly is nice, but I really see their true value as being an in-between between other systems. Despite this, I haven't yet come across a paper that has seriously tried to combine this scheme with another. I'm guessing that it's hard to get the relevant interaction that would preserve the quantum information. Without this, it may be difficult to compete with other schemes. Coherent spin-photon coupling was achieved in 2018 by Landig and colleagues, so we've already seen an example of a flying qubit half a decade ago. However, the ability to microfabricate many channels that can run in parallel, as was seen in the 2011 Bradbury paper, would be a huge advantage over photon coupling if it could be achieved. Also notable is its dependence on low temperatures, which is an issue that flying photonic qubits don't have. These are citations for the papers I specifically referenced, and links will be provided for each of them in the description. And with that, I'd like to thank you all for watching.